Hello, ladies and gentlemen. Today we're going to talk about the problem called peak index in a mountain array. So the problem says you have an array of mount if the following properties hold. So the least amount at the length your array would be 3, greater or equal to 3, and this condition should exist. So what kind of condition is this? Is that basically it's like a mountain where 1, 2, 3, 4, 5, and then this is the peak of the mountain. So the peak of the mountain is kind of like increasing order, and then the right side of the mountain should decrease, right? So that's what they mean by, so it should be like 4, 3, 2, 1. So yeah, so and you have to return the index of 5 because 5 is a peak. So it's kind of like, it's like a mountain, so it's like this, and that, and the same way on its right. We have to take it down like all this. So anyway, so it's a problem, and we have to return the index. And the brute force way of solving this problem would be to just scan it one time. So 4, 3, 2, 1, and so scan it one time. You start at 2, and compare the I. No, you start at 0 and compare the I with I plus 1. So the condition is when you see the element that is when you see the element that's greater. Okay, so this would be a okay. So if you start from here and you compare it with I plus 1, and when the position array I is greater than position I plus 1, that would be then you just return the answer, because over here I is not greater than 2. The only time it will be greater when you reach the peak, and it will be greater than 4. So this is a brute force solution to this problem, and here's how it looks. Let me go to my submissions. So accepted one. So here's how it looks. It's very simple. Alright, so here I think I'm checking like the left and right, but the left is unnecessary. So the better approach, this one would give you order of n, but the better approach would give you log n, because we could use a binary search in this problem. So if I go to my submissions, so in a binary search, if you're trying to understand a binary search, I really recommend go ahead and read about it. And if you go to this problem and go to solutions, we'll give you an article about binary search. There are like 3 templates, different ways of using a binary search. So like you click on this link and you get to this, and you just read about it, and there are like 3 templates. The first template is regular binary search, where you are searching for a number. So if I go click on this, like if this regular binary search where like mid plus, you skip the middle, here too. So and then you only care about the middle, and you're just comparing it, and at the end, so the compare it should be left less or equal to right. This is the first template, but for our solution we have to use a second template, which is more of advanced implementation, where you care about you care about the immediate right neighbor's index. So why do we need that? If you go back to the problem, here we have so if you say 1, 2, 3, 4, 5, and then 4, 3, 2, 1, you notice that this is increasing. So there's a I, and we in binary search we have to compare it with its neighboring which is the right one, so we are going to compare it with right one. So we compare the middle with I plus 1. So if array I greater than I plus 1, so what does it mean? So let's say I hope you guys know how binary search works, but the thing you do first is pick a left, which is 0, and the right, which is length of array minus 1. And so what we're gonna do is, while left is less than the right, and so we have to find the middle index every time in binary search, and what we have to do is say left plus right minus left divided by 2. So once you find the middle, and our condition is, we say we are comparing with a neighboring, so what we would do is, if array middle is greater than array middle plus 1. So that's why we are using the second template instead of using this first template, because second template is different. You do mid plus 1, and then for the left and for the right you just do mid. So while in template 1 we were skipping middle, here you don't skip it. So and then at the end you have one element left, was using a template 2. So let's go ahead, and so if middle element, if at middle greater than middle plus 1. So let's look at an example. So for example, if our middle is like 3, right? So 3 would be greater than 2. So at this point, however, our answer is 5. So in this case, if we find an element where the element is greater than its right neighbor, what we will do is we're not gonna skip the middle, because what if the middle was 5, right? And if we skip the middle, we would have skipped the answer. So that's a logic with template 2, because for example, let's say right is here, left at index 0, right? And so currently the 5, let's say 3 is the middle. If we compare it with a middle, if middle is greater than middle plus 1, which is true, we will say right equals to middle. I wouldn't say middle plus 1, because I don't want to skip it. Because if my middle was 5 and I did middle plus 1, then it would skip middle. If I did middle minus 1, it would skip the 5. So that's why we just make the right be equal to middle, so it'd be equal to this index. So after that, what if it's not? So what if we are at this position, at 3 for example, and array middle, which is 3, is not greater than middle plus 1. So apparently looks obviously 3 is not greater than 4. So what do we want to do? Then we're not gonna make our left equal to the index of 3, because we know this is not the answer. So we're just gonna skip it completely and go to the next one. So how do we do that? In order to do that, we are gonna just say left equals middle plus 1. And at the end, what happens is that you're gonna get your left would be come to 5, and your right will also be at the same position. And what happens is you just and then your while loop stops running, and you just return. You could either return left or right. So I'll just say L. So let's say how this algorithm works. So at the beginning it would be L here, right here, and then what happens is that the first time you pick the middle would be 5. So middle would be 5. As you see in this binary search, we're not like comparing if it's equal or not, because we don't know yet, because we're comparing it with its neighbor. While in a just a regular binary search where we're trying to find the target, we only care about middle, and if it's equal to the middle, we just return it. But however, here it depends on its neighbors, so depends on the positioning of neighbors. So now currently we have middle. Now I'm gonna compare. If middle is greater than middle plus 1, it is, right? So now what I'm going to do is right equals to middle. So I'm going to bring right to middle. So now right is at index 5, at index of the current value, which is 5. And the next thing what happens is that it picks another middle, which would be 3, right? So, and then I compare it. If 3 is greater than middle plus 1, which is 4, and 3 is not greater than 4, so which means that my left was going to skip 3, and my left would be at this position, right? Because middle plus 1, and it goes to this position. So the next one, left is still less than the right, so our condition is true, so it's going to go and picks middle element again. So the middle element in this case would be it's going to pick right. So at this position, and we have left and right, and then we have a medium, and so it's going to check if oh, I think it picks this position. This the left would be medium, and what it's going to do is that it's going to check if 4 is greater than 5. It is not, so it's going to go left equals middle plus 1. So our left would be equal to the position at the current value, which is 5, and then at this point the condition would be false. The while would no longer run, and return L, which returns the index of current value, which is 5, and this is our answer. So that's it with the binary search, and this has a logn. This has, so let me L. So this is has order of logn, which is better than linear one. I think we are good to go. Let's run the program. Awesome, and I will just submit it, and you can see that it's gonna run. See, it bit 100%. Anyway, so this is a better solution to this problem, and I'll see you guys later.